Alright guys, so your 7-6 lecture is on what happens when our eigenvalues are complex and we're trying to solve an equation. So last time I did a general solution example, so this time we'll make it an initial value problem. The difference is on this one we're going to end up with some complex eigenvalues. So remember the solutions of x prime equals ax are the same as the solutions, not the same, but they correspond to the eigenvalues and eigenvectors. So we need to take the determinant of a minus lambda I and set it equal to 0. So that's 1 minus lambda, negative 3 minus lambda, plus 8 equals 0. A little bit of algebra later, we get lambda squared plus 2 lambda plus 5 equals 0. So lambda equals negative 2 plus or minus the square root of 4 minus 20 over 2. So lambda is going to be equal to negative 1 plus or minus 2i. The deal with complex eigenvalues, so long as our matrix was real anyway, is that they're always going to occur in conjugate pairs because they come from solving a quadratic equation. So we're going to get the plus or minus the same thing, I. And when we plug them back in to our equation, to our matrix, so I'll have 1 minus, and then we can pick either one. We'll take the plus one here. Negative 1 plus 2i, negative 8. 1, and then negative 3 minus negative 1 plus 2i. When we row reduce this, we get 2 minus 2i, negative 8, 1, negative 2 minus 2i. Now, just like before, we can row reduce this. We know these rows are going to be dependent, so either one of these rows can be zeroed out. If I take 2 minus 2i times row 2, it'll be equal to row 1. So this will row reduce to 1, negative 2 minus 2i, and just take the other row as zeros. In other words, you can pick either row you like better, and you know the other row is going to row reduce to zeros. You don't have to do the row reduction. That's why we did the determinant set equal to 0, to save us that trouble. So from this, we have that k equals, let's see, how about 2 plus 2i, 1. Right? 2 plus 2i times 1, 1 times negative 2 minus 2i, add those up, you'll get 0. Pardon me. So, to go with lambda equals negative 1 plus 2i, we get the eigenvector 2 plus 2i, 1. If we were, pardon me, if we were to repeat this process for lambda equals negative 1 minus 2i, we'd get k equals 2 minus 2i, 1. I'm going to leave that as an exercise for you if you want to verify that by going through this process. But this is always true. If, pardon me, if lambda equals a plus bi is an eigenvalue, and k is the corresponding eigenvector, then lambda bar is also an eigenvalue, with k bar an eigenvector corresponding to lambda bar.
So prepositional phrases are modifiers. Let's review through this.
So that means that we can write our solution, or a solution, as x1 equals, let's see, what was that? K was, I just had it, hang on, moved my paper too far. 2 plus 2i 1 times e to the lambda t, right? That's always the thing. So lambda in this case is minus 1 plus 2i times t. And x2, the k for x2 would be 2 minus 2i 1. And the lambda with that is negative 1 minus 2i t. So those are both eigenvalue-eigenvector pairs, or I'm sorry, those are both solutions, but they're complex, and we would rather have some real-valued solutions. So there's a couple of things that we can do with this. We can define a new x. I'm going to actually call it y. I hope that's okay. I'm just going to define y1 as the real part of x1. That's also the real part of x2. And y2 to be the imaginary part of x1, which is the opposite of the imaginary part of x2. Now, my claim is that these both also work, but y1 is 1/2 x1 plus x2. Right? The real part of x1 plus the real part of x2. The real parts of x1 and x2 are the same. And the imaginary part is going to be 1 over 2i x1 minus x2. So all I'm saying here is that this y1 and this y2 are a linear combination of this x1 and this x2. Now I don't have it all written out for you so that you can verify that yet, but we're going to actually kind of see how that works out in just a second. I'm just saying that since you have a conjugate pair, you have your lambda has a real part and an imaginary part. Your your k has a real part and an imaginary part, and they basically are the same. There's a sign difference, right? But that's it. And so we can take linear combinations of these complex solutions to get real solutions, and that's what we're going to do here in just a second. So let's go ahead and look at what x1 looks like in its full form so we can see what we're doing. So x1 can be written as e to the minus t times 2, 1 plus 2, 0i, that's my k, times e to the, so what I've done here is e to the minus t and then e to the 2it. So remember, e to the 2it can be split into cosine 2t plus I sine 2t. And so I've already pulled the e to the minus t out front, and here's the cosine 2t plus I sine 2t. If I distribute these out, then I'll get that, leave the e to the minus t alone, I will get 2, 1 cosine 2t, I'm going to need a big bracket here, 2, 1 cosine 2t.
And it does, you don't have to tack on at the end. You can add it.
And then I'm going to go out of order here. I'm going to take the last next because my i's are going to cancel when I do that. So then I get minus 2, 0
In the closet.
sine 2t.
Write that down.
And then the outer and the inner is going to give me plus 2, 1 I sine 2t plus 2, 0 I cosine 2t.
Okay, and that modifies code.
So the real part of x1 is this multiplied by e to the minus t, and the imaginary part is this without the I multiplied by the e to the minus t.
Everyone but nobody.
So what did I call that? I called that y1. y1 is going to be the real part of x1,
That would be an adverb.
which is
You'd be modifying
e to the minus t
they realize.
times 2, 1 cosine 2t minus 2, 0 sine 2t, and y2 is the imaginary part of x1, which is e to the minus t times, let's see, let's write that in the other order. How about 2, 0 cosine, keep our cosines together, plus 2, 1 sine 2t. Remember, the imaginary part, that should be a parenthesis, doesn't have the I on it. We're talking about the coefficient of I. So that's where the I has gone. So these two things, y1 and y2, are solutions of our original equation. The original equation, x prime equals this matrix times x. Now, we can take the Wronskian of these guys, probably not too hard here. Remember, we can take the Wronskian at t equals 0, because the Wronskian is either always 0 or never 0. So I know that's not good notation there, but we're going to take the Wronskian of these two solutions, and that's going to be the determinant of y1, but at 0, and then y2 at 0. So y1 at 0 is going to be, let's see, we're just going to get 2, 1, and then 2, 0 for y2 at 0, right? When t is 0, sine is 0, so that's going to 0 out those two, and that's going to just be a 1 in front. Cosine of 0 is 1, so we just have those two vectors. And that's going to be equal to negative 2, which isn't 0. So the Wronskian's not 0. So these two solutions form a fundamental set. So x, our solution, our general solution, is c1 e to the minus t times 2, 1 cosine 2t minus 2, 0 sine 2t plus c2 e to the minus t times 2, 0 cosine 2t plus 2, 1 sine 2t. Now, we had an initial condition. That's back 2 pages, hang on. Our initial condition was that x of 0 equals negative 2, 1. So x of 0 is equal to c1 times 2, 1 plus c2 times 2, 0, and it was equal to negative 2, 1. And we can solve that any old way you want. But I think the easiest way is to go ahead and just write the system. So that's 2c1 plus 2c2 equals -2, and c1 plus 0c2 equals 1. So c1 equals 1, plug that in, we get 2c2 will be equal to -4, so c2 is equal to -2. And so our specific solution here to this initial value problem, oops, not of 0, let me start that over, x equals, c1 is 1, so e to the -t times 2, cosine 2t minus 2, sine 2t minus 2 e to the -t 2, cosine 2t plus 2, 1 sine 2t, which can be simplified. So let's do that. So let's take everything's got an e to the t here, so x equals e to the -t, and then let's do our cosine. So we have 2, 1 minus 2 times 2, 0 cosine 2t. Let's see, minus 2, 0, let's go ahead and factor that out, 2, 0 plus 2 times 2, 1 sine 2t. So that's e to the -t times, that'll be 2 minus 4 is -2, 1 cosine 2t minus, that'll be 4, 6, 2 sine 2t. So that is the solution.
Each underlined prepositional phrase, and then they want you to
Let me find that actual problem again. You guys have it all in your notes, but I flipped several pages, so just to cap it up, x prime equals 1, -8, 1, -3. X with initial condition x of 0 equals -2, 1. So the main thing to take away from this when you're talking about complex eigenvalues is that finding that second eigenvalue is actually completely optional. We really only needed x1, right? We take the real part of x1 and the imaginary part of x1, which is basically the same, and they'll have the same real part as x2, and the only difference would be an opposite of the imaginary part of x2, and any constant multiple of a solution is a solution. So that gives us our fundamental set of solutions. That's exactly what we did here, right? We just took x1. So we only worried about lambda 1, we only worried about k1, and so your fundamental set of solutions is the real part and the imaginary part of that first solution you find. After that, of course, if you have an initial condition, you have a little bit more work to do. Let's see. I am going to, so this question also asked us to sketch the trajectory, and I am going to have a hard time replicating that in my first try. So let me actually just kind of walk you through the steps. So the first thing is, it was talking about behavior of the solution. And let's pull up the solution. Where did that go? There we go. So the solution, as t approaches infinity, this part is bounded, right? It's constant vectors times sine and cosine. Those are never bigger than 1 or smaller than -1. So the biggest this parentheses can be is the sum constant vector, fairly small. And e to the negative t is going to 0. So our solution will be headed toward, will have magnitude 0 as, or will be headed toward having magnitude 0 as t increases. So it's going to be spiraling in toward the origin. Now, I'm going to be real honest. Using a calculator, using an online graphing thing, totally fine for this. I am not going to ask you to sketch a trajectory. Even with the take-home test, I'm not going to ask you to sketch a trajectory. For your homework assignments, we want you to look and see what these kind of look like. There's a discussion in your book, a very brief one, about using direction fields. The idea is you treat x2 like y and x1 like x, and you divide your x2 prime by your x1 prime. You can do that from your matrix equation, and so you get this kind of a transformation. And
you want to start taking that
sorry, when you do that, you can sketch a direction field. Now, I again don't think you should do this by hand. Your book uses these to kind of explain what's going on, and you can kind of see that spiral effect from the direction field as well. But this is a graph of the particular solution that we found. The where did it go? That one. E to the negative t times this vector cosine 2t minus that vector times sine 2t. All this is just writing it back out in parametric form. So I'm not super worried about trajectories. This is not a part of the class that I get real excited about, and all things considered, I think it's a nice thing to mention but not emphasize. So you don't have to worry about trajectories on your test. You definitely don't have to worry about direction fields on your test. As a matter of fact, I've got notes from other instructors that talk about all of the web apps and things that they use to do direction fields and trajectories. Nobody does these by hand. So that said, that's really all you need to know for 7-6. Just that first when you've got a complex eigenvalue, just use one of them. Use the one with the plus if you prefer the plus. Use the one with the minus if you prefer the minus. It doesn't matter. That's going to lead you to one eigenvector. Take the real part, take the imaginary part of the solutions that go, the one solution that goes with that eigenvalue eigenvector pair. Good luck.